Hello Jim and other examinators. Today I would like to show you what I've done for my final year project. I've been working on an extension to Unity which provides a very easy, non-resource consuming, very efficient system for pathfinding for creatures in a survival horror genre. This system doesn't rely on procedural figuring out of paths by the creatures. Instead, it pre-bakes the paths from one node to other ones. It pre-bakes them prior to the game release. That means that creatures won't have to spend time to recursively search for the path from one node to the other node in order to get from one room to the target one. Because of that, during runtime, it is possible to drive many creatures, up to 500, maybe 1,000 of creatures, in parallel, and they don't search for their paths, nothing like that. They just make a query to their local node, saying that, okay, you are my local node, you are the closest one to me, please give me the path towards my target one. And if during the bake process the path was stored and precompiled prior to the start of the game, then the path will be supplied to the creature, and the creature can start to advance through a series of waypoints that this path provides. I'd like to show you what I've done here, and it's just a basic scene which I made in 3ds Max in a couple of days. I've light mapped it, and this is where the creatures will be running around. I wanted to make a scene look quite intricate, to have many paths, so that the creature can get to their destination via different paths, alternative ones, just to show the versatility of my pathfinding solution and the speed at which it operates. Creatures can go around like this, they can go up and down via the ladder, they can go through the door, for example here, or go through, maybe rise up the tower via the spiral staircase and enter the building from other two doors, for instance. And then there is a ladder which is leading upwards to the top floor. Well, you can open the scene and you'll see for yourself. Hopefully it's decent enough. I made a couple of little endpoints such that creatures can enter the tent, for example, and stay there, but there is only one-way entrance. However, many places can be reached by going through different paths. First of all, I'll show you how creatures navigate through the environment, and then I'll show you how easy the tools that I made are to set up the whole system and why it's user-friendly. This is the editor window upon which I was working. It presents all the GUI, the graphic user interface, that the designer can be using, similar to 3ds Max or Blender or other 3D modeling programs, to quickly shape out the nodes and their shapes, and I'll be showing this to you later on again. But my whole point of creating the system was to simplify the whole process of creating and setting up, so that the designer doesn't have to enter any kind of numbers. He doesn't care about typing explicitly the relations. For example, this coordinate is tied with that coordinate, which would take immense time and would take forever to set up. Instead, he can just drag around nodes, click the bake button, make sure that the nodes have the correct shape and are pretty much connected to each other visually. Click bake, and the whole system will do everything behind the curtains. I've already baked the scene. If I unclick hide nodes, you will see that my scene is scattered and filled and populated with the nodes. One of the rules for my nodes was that every single one has to be convex. For example, it cannot be L shape or C shape. It can only be square, or it can tend to circular shape. Also, because I'm implementing a three-dimensional system, it was important to ensure that creatures can quickly navigate themselves and locate themselves, figure out which node is the shortest one and the closest one to the creature, and I'll explain how I do this shortly as well. For example, let's say we want the creatures to come to this node. So I'll select it, and I'll copy its name, which is a string, just copy it, and we'll start the game. Let me then select some other node which is far away, for instance this one. Or I can select one of those two which are in here. So I'll select them, and my window provides an option where the name of the target node can be entered. So I'll select everything in here, Control A, to make sure that everything is selected, because if the name is entered incorrectly, creatures will just stand on their spot wondering what was this node that has incorrect name. So I'll paste my target name into here, and with this node selected, I'll click Deploy Creature. As you can see, we got a capsule which is representing a creature, and it advances towards the target node, which is here. It's picking this path as its closest one, and it's gonna go around like this upon the spiral, and will find and finalize its path on the very top of the tower. It's going right there, and for debugging purposes I provided creatures the same speed, so they won't have any varying speed, they'll be just advancing with the same velocity. So we can create many of them. Let's select this node, the old one that we've been using before, and deploy many creatures. Notice how they arrange themselves. They don't go through the one single point. Instead, they try to balance their traffic. They try to spread themselves out evenly using multiple waypoints and gates. If I click Show Waypoints, you can see that every connection between each of the nodes contains several waypoints, and I'll show you how they can be altered in a second as well. But creatures are going from this node to the top one, and they'll be going through the waypoints and will be moving up and down depending on the surface, which is representing the floor engulfed by this node. So if I throw, for example, creatures into this node and just toggle off my show waypoints, so I'll throw creatures into here, and because they still have the same target, they'll keep going onto the top of that tower right there. And we can place creatures here as well, for instance. They'll be going down, and some of them will probably pick this path, I think, because all the paths were sorted out and pre-computed and chosen due to their length. So there are many paths from how creatures can reach the top node on the top of that tower from that one. There are many, many ways, literally hundreds and thousands of ways. But all of those ways are probably too long, and there is only one with the best length. So instead of going like this and descending upon that tower, they just decided to go straight down and exit through the door over here. They'll be going along this ground, and then they will be going upwards along the tower as well. I'll stop the game, and everything will be reverted back to normal. Because Unity is written in C++ language and only exposes C# to work with for ordinary designer like me, it was very difficult and very important to ensure that all the data, that is, all the relations between the nodes, all the parameters and variables of creatures, it was important that all of this information was stored and persisted through the sessions of Unity. For example, if I restart the game, all the entries that I've entered here and all the data that was stored between nodes will be wiped if it was written incorrectly. Unity does not know about any kind of custom classes such as dictionaries. It doesn't know about complicated polymorphed classes. The only thing it works with is basic stuff like linked lists, arrays, and just basic plain classes. However, in order to store my information, I had to go through a severe process of handling all of that data and passing it to Unity's core, which is written in C++, in a separate way. I've written my own serialization codes. I'll quickly point them out in a second, how they are handled as well. But all of this huge data that is stored right here, all of the connections, all of the paths, are managed to be transferred from one session to another. And if we close the scene, or close Unity, and come back and open the scene, everything will persist as it was saved. It was also a challenge to ensure that all of the nodes are shown differently in different scenes. This project was achieved with some basic stuff that Unity provides. For example, for navigating of creatures, I used some of the Unity's API, such as transform function, pretty much all the stuff that we learned in the game module. But apart from that, I didn't use any kind of Unity's provided pathfinding system. In fact, it wasn't suitable for survival horror genre, and that's why my whole project started. And I was operating with my own arrays of data, arrays of vertices. I was shaping out the relation and keeping an eye on how the vertices are adjusted. I was creating complex structures which define the floor, and I was calculating the planes of each node. I promised that I'll come back for serialization, but right now I'd like to show you what happens if I open a new scene, or perhaps maybe drop a node into here. The way it works is, inside of my project panel, there is a folder called Igor Aherne Tools. And there is several of scripts which are very important and upon which my system operates, and also one in the editor. If I select Igor Aherne Tools and drop the node into the scene somewhere here, I'll be able to manipulate it. The node is always convex, it has to be convex, otherwise it will be shown as problematic. And it has to be shown as problematic, otherwise the system will fail. However, with the convex nodes, with several of them, we can create concave shapes with no problem. I can just click on Insert a Segment, and there are spikes which are signifying that a segment can be inserted there on all three sides. So I'll click on this spike, and this will place a segment, and the whole thing has lit into a red color temporarily, because it's saying that the zone becomes very close to being concave, which is bad. So for example, this would be concave. But as soon as we take this segment out, the zone colors itself, saying that it's alright. And the more convex it is, for example here the most convex shape would be cube, the more green the zone is. And the more dangerous any part of it is. For example, if we bring this vertices closer, this part becomes quite close to being concave. I'm computing dot products of vectors. If two vectors from several of the vertices are perpendicular to each other, I know that their dot product will be close to 0. And if they are quite parallel to each other and are facing in the same direction, this is a clear mark that the zone is concave and should be fixed. But the dot product would be 1, for example, in that case. And that's how I pretty much operate on my nodes and see if the zone should be colored differently, if the color should be interpolated to some other, maybe yellow color or bright red, if the dot product is 1. I had quite a lot of fun with shaping out the zone, and because this is a procedurally generated mesh in Unity, I had to follow some strict rules and figure out in a clever way how I can configure and store the data of this node, store the mesh data. If you have a look here, I've got numbers saying 6, 0, 2, 4. And on the bottom it's 1, 3, 5, 7. The way I was constructing the zone is I was supplying the vertices in the following order: 0, 1, 2, 3, 4, 5, 6, 7, but in a zigzag manner. That means that their coordinates in space would jump up and down, and that way I guaranteed myself that all of the even vertices are always going to represent the top, and the odd ones are always going to be at the bottom. Because of the nature of the nodes and the rules that my system imposes on the structure of itself, the walls have to be perfectly straight. However, we can slant the top and bottom planes. For that we have to select two anchor points that will represent a segment, a vector, along which a plane can be computed. And then we can grab one of the other remaining circles by the border, by the red one. So here we would be clicking on the blue circles, and here we would be clicking on the red outline and dragging up and down. This allows us to slant the plane, and if we pick different anchor points, for example those two, you can see that the plane is altered in this way. Because of that, I simplify my life by a big amount, because in order for the creature to find if he's inside of the zone or outside of it, all he has to do is to look strictly from top and figure out if he fits into this square or rectangular shape or convex shape, and then compare his Y position against the Y coordinate of the top and bottom planes. If all of those checks are true, then we are inside of the zone. Otherwise, if we are outside of the square, we must be somewhere around the zone, and we don't even check about height of the node, simplifying and speeding up the work process by a big amount. But if we are inside of the square and we fail, for example, the check, and we find out that we are above the top plane, that means that we're above this zone and we should search for another node. Initially I had a very interesting idea of letting the user not focus about clicking on those anchor points. Even though it doesn't take that much time, I thought that it would be awesome to make the system predict the way that the user wants to position and tilt the plane. So for example, there would be no blue spheres available and we wouldn't be able to set the anchors, but the user could be able to drag the red circle and the system would pre-compute or try to guess where would those anchor points be. However, it turned out to be very complicated, And most of the time it was completely wrong, because even the most correct choices, sometimes the user can do some weird stuff that the system can't guess. And with that approach, it would be very difficult to revert the state of the plane if the user made a mistake, because the planes would become distorted as the node tries to guess how the plane should be allocated. And sometimes this can lead to drastic results. So I decided to take a safe path, and just to take a couple of seconds, maybe half a second, of user quickly clicking on those blue circles and dragging one of the anchor points up and down. This is so because in order to compute the equation of the plane, the system needs to know about the tangent, that is the vector which is parallel to the plane, and also a point through which this plane passes. The point is being the displaced vertex. And as soon as it's displaced, we take a look at the anchor points and draw a plane. And then for any other points, for example that one over there, when we already know the equation of the plane, we can just say, okay, for that extra point, its x and z coordinates are that and that, so please give me the correct interpolated y coordinate, so that it can be represented as lying on the same plane as those three vertices, the anchor ones and the displaced vertex. Of course, if we adjusted the zone, for example, to that shape, and we want to click and adjust the area and drag on the cubes, the whole plane has to be recomputed every single time the vertices are moved. Because if they wouldn't be recomputed, then the plane would be it wouldn't be a plane. The top part would start to bend. For instance, if I jump to 3ds Max and quickly show you what I mean, have a look at this. We literally just imitate what we've done in Unity by slanting the top of the plane. However, if we begin to move this segment inwards, then the whole thing becomes bent, and it's no longer a plane. Those two vertices should have been adjusted to fit on the top plane. And this whole system has to be done for bottom and top as well, and I ensure that it's done with performance in mind. So I don't just recompute the planes every single time, but only when there is a change in the position of this segment or any other segment is detected. My whole system tries to avoid constant heavy computations and instead only performs them when something crucial happens. For example, variable changes or some kind of value gets altered. With this zone, we're able to create other zones nearby. So I'll click on Create Neighbor and stick a couple of other neighbors into here. We can also insert the segment and adjust the area. Now initially, while we haven't pressed the Bake button, those nodes only know about their direct neighbors. So I'll open up the rollout and I'll hover over this button. This is exactly what the neighbor of this node is. If I click on this button, this is another functionality that I've incorporated, then we switch to another one, and it only knows about the two ones. When we adjust the area, something interesting happens. Since this node only knows about its neighbor, and this node knows only about this neighbor, this node and that one have no idea that they are connected through this segment. However, this information has to be kept, and that's where an idea of touched nodes came into play. When we adjust the segment, there is some sort of displacement for 2 and vertex number 3 at the bottom, which has to be imposed on the neighbor of that node, but also on the neighbor of that neighbor and on its neighbor. So when we're creating a node, we also check if there are any kind of other neighbors of other neighbors, and we store those neighbors of neighbors as touched nodes, so that later on when we move the segment, the segments of the touched nodes are moved as well. It's very interesting how those subtle things I never thought about, and I discovered them to my huge amazement. And looking at 3ds Max makes me wonder how they make such complicated things. But this is how I handle information. When we create the neighbors and the nodes, we also create some sort of entities, the virtual ones, which are called mediums. Mediums are the connections between the nodes, and they contain different waypoints. And as you can see, the waypoints are shown with the lines here. I can increase the number of waypoints between the neighbors by clicking on this square, and this will adjust this virtual entity, the waypoint that is currently stored in the project in the resources folder, and I'll go over this again later on. But we've increased the number of waypoints, and here we have 5 of them, with 3 waypoints on the other side of the other node. And if I slant the top and bottom for that node, by picking, for example, those two anchor points and bringing this one down, you will see that the waypoints are stretching themselves, and they represent the elevation from that node's floor to the floor of that node. So the creature will have to go along the floor, and then when he picked the waypoint, he can just go up that waypoint and proceed to the other waypoint as well. Maybe there is a slant occurring here. The waypoints are figuring out if their height is negligible. For example, like this, it's negligible and becomes green, and otherwise it's just showing as blue. That means that the full ascending of creature will occur in there, and it will have to perform a climb. There is also a need to ensure that the system is loopable. If we just create the tree structure like this, keep creating the neighbors like so, in order to get from that node to, say, very right one, creatures will have to go along that path. And there is no alternative path. But we want to have loops in here and create possibility of alternative paths. That's why I will shape out the zone like this, and will show you how I can do bridge. Bridge is another algorithm that I was working on for quite a while, and it guesses, which I'm quite proud of, it guesses where the user wants to bridge, between which faces of nodes it wants to throw another node. I will quickly fix the bottom plane of that node, just to have a correct look. And if I select that node, for instance the green one, and pick it as node A, it will highlight itself with blue, signifying that blue is the blue button picked A. And I will also pick this node as well, as a purple. We can see that there is a ghost node representation which hasn't been materialized yet, and it's saying that if you press bridge A and B, that's where the node will lie. And it guesses where the node should lie, because if we make it less evident choice for the computer, it will go for a better result. For instance, like this, it's picking up that node over there, because the zone is more convex than if it would be making a node through that connection. There are several of ways through which it connects. There is this way it can connect through it. It can connect with this face and that one, or it can connect like this or like this. So it always 4 choices, and it picked this one. If we now click bridge A and B, it will throw a node in between of them with pre-computed top and bottom planes as well, already everything defined. If I show you the waypoints also were created and pre-computed by the system. So I think I should just correct the plane structure of this node to be of a more correct shape, and maybe adjust the areas so that other nodes are not as red. Like this is alright. Now there is several ways through which creatures can get from this node to that one. They can go to the right or to the left. And the whole the complexity grows as we have more and more rings, more donuts. Because sometimes, if there are 4 donuts, for instance, there can be 16 ways, 32, 1000 ways to get to this desired destination. But having this structure and having our waypoints set up, we can now bake this little system with, let's say, the depth of 6. That means that when we're storing and trying to find the correct paths for this node, it will start to inspect the neighbors of neighbors of neighbors, but it won't go further than 6 neighbors. And we can gradually increase this number to make sure that we find the paths to all the nodes, instead of just saying, okay, billion depth, and then it will take forever. But if we do this way, we'll be able to compute paths very, very quickly. I'm making use of multi-processing or multi-threading, so that every single node finds the paths to all other nodes on its own separate threads. We have how many? About 10 nodes here. We'll have 10 parallel threads, each one computing paths for its own node. Let's click bake, and you can see that there is a green flash line, which was displaying the progress of nodes being baked. If we have many of them like here with depths of 60, it will take about 10 minutes to render, instead of 5 hours if it would be without multi-threading. Multi-threading took me quite a while to figure out, since Unity doesn't really want to contribute to multi-threading in any way. Its exposed C# code is not thread friendly. So I cannot use any kind of Unity's API such as transform or access the mesh components, get component, nothing of that. I can only compute my own arrays and my own resources on each of the threads. So I had to pay close attention to debugging, since if threads are being ran and some error happens on them, and it's quite a long process for each thread, it's very difficult to find where the process occurred, because I could not use debug, since Unity's API is also including debug. I could not use debug, and I should have, and I spent a couple of weeks polishing that system. Now the interesting part happens is after we click bake and unfold this foldout, we have different reachable nodes that we can access from this one. If I hover over them, you can see that there is a red path line, which is showing you which waypoints should be taken by creatures. Creature to get from here to that node over there would have to go through those nodes. Of course, while there are different ways to get to nodes, for example, through the left side or through the right one, and we have, for example, two paths between which we have to pick, there are also several waypoints on each path. So do we go for, if we say inspect the left path, we can go from the center waypoint to the left one, to the left one, to the left one, and pick the left ones. Or we can pick the center one, go through the center one, go through the center one, go through the left one, or go through the right one and then through the right one. Which one do we pick? Right here we got 1, 2, 3, 4, 5, 6 connections, and each one of them has 3 waypoints. That means that 3 to the power of 6 searches has to be done, and comparisons has to be done in terms of distances, potential distances, such that the quickest one can be chosen. And I've made my own implementation, which I'm very proud of, which allows us not to compute in this order and to the power of number of mediums time, but instead into the linear time, so that if we have several mediums in here, we can compute with that speed. And because of that, I'm able to quickly sift through many ways through which this path can be expressed to find the shortest one, and then inspect the same way the right one and find the shortest waypoints sequence as well, and then compare those two shortest sequences to finally figure out should we go through the left path or should we go through the right one. And I'll be talking about this in my report. But now the creatures can be deployed as the game is ran into this node, for instance, by clicking deploy creature into that one, and we'll pick this node, copy its name, Control A everything in here, and just paste it into there. And the creatures are going through the path, which is this one, pretty much what was shown by the system. One thing that I found through my user testing was that users wanted to have irregular shapes of ground to be expressed and followed by the creatures. Because my nodes represent the flat surfaces on the bottom and on the top, it means that if they take the path, they'll be going in a straight line. And if we have hills, let me hide the nodes, for example a pit in here, we cannot really express it through our nodes because the paths will be very straight. Maybe if we incorporate many nodes, but my system doesn't really provide an option of cluttering them and making clusters of them. I had to make a way of computing the ground which is underneath of the zone. For instance here, do we use several of nodes or do we use just one? This is what my users insisted on. And if I unhide the nodes and select this one, you can see that it's a single node with a straight surface at the bottom, straight plane. But what I want to show you is that if I click edit floor cells, you can see that the whole system interpolates the floor underneath of it. It contains a jagged array. That means that not a two-dimensional array, which would be of fixed size and some of the points would be wasted. Like here, for example, top right corner would be wasted, and sometimes it can be as bad as half of the array is wasted. Instead, I'm using a jagged array, which means that it's an array of smaller arrays of varying length. And that way I'm able to follow the floor and the shape of the zone. But for example, if I click on edit floor cells once again, I've added the functionality which was also insisted by my users, that there has to be a way of changing the resolution of the floor for each single zone separately. And sometimes it can be very heavy visually, because Unity cannot draw those many points efficiently. So I just provided a possibility to turn the visibility off, but still have it there. This whole system interpolates the floor and makes several raycasts towards the ground if the zone has changed. to pre-compute and reconstruct its own array of interpolated floor heights. Let me show you what happens if I slant the bottom of the plane. For example, like so. You can see that the black points are everywhere where there is no collision with the floor. And the green ones mean that the height from the plane to the collision is not very big. But if it gets to red, it's saying that, oh, it's going to be bad if you continue to bring this plane downwards because of my optimization technique. Since it would be very resource consuming to store float and integers in the arrays, instead I just make use of the byte, which is just 8 bits for each single cell. That means that I can express the values from 0 to 256. And because of that, every single zone weighs about, I don't know, 100 bytes, maybe 200 bytes at maximum. I can express the same thing in here by creating, for instance, a sphere, 3D object sphere. Make sure that it has an appropriate collider, or in most cases mesh collider. I will scale it upwards like so, and will position it inside of my nodes, like somewhere here, for instance. It has to have a layer of Igor Aherne AI surface. This is a must, so that the system can compute itself. If the plane is way too low, the points will snap because there is no way to express more than 256 centimeters above the surface. So we have to bring it upwards so that the floor can be grasped once again by our bytes. 1 in this 256 value range represents 1 centimeter. So we can express an elevation of 2.5 meters above the plane. And the creatures will be going, when they're going from one waypoint to another one, they'll be looking through this array and finding their neighbor cells, neighbor floor cells. So if they are here, for instance, they will look through the 9 surrounding ones and will interpolate their heights respectively. This is interesting because how do I interpolate between the center point and the surrounding ones? Because they have different lengths. I found out the way that I could use the radius, which is equal to the distance between those cell points. And based on the ratio of the radius to the distance of the surrounding waypoints, I can calculate the coefficients for every single one, and then apply those coefficients to find out an averaged height of all of those 9 points based on their coefficients, so that the creature can have its own, can maintain the correct height, interpolated height, as it advances through the array. If I click on here, we get a warning that, well, there are black dots here, so we should bring the plane upwards a little bit, or bring the sphere downwards. But 2.5 meters is way than enough, and it allows to express wavy surfaces, so that creatures don't tend to go through the hills, the tiny surface elevations. Instead, they are floating above them. Let me click bake once again with a depth of 6. And I will click play. Sometimes I have to click on the window to refresh it after the game was started. And I will deploy a creature into here. And let's say we want to go into here. Or actually, yeah, it's going to take the left path, so I'm going to drop a creature into here. As you can see, it goes up the sphere and down the sphere, interpolating its height. And the higher the resolution is, the more smooth the movement is, and the less wavy effect will be. We are interpolating using coefficients, so the creature will not be snapping up and down like if it would be raising on ladders, as it was initially. Also a request from my users. Now it's interpolating using coefficients, and it's moving smoothly along the surface. But we can increase the resolution or decrease it, and then it will be it will have its effect on how the creatures are moving along the surface. For instance, I'll click on this node, copy its name while still playing the game, and we'll re-enter the name, and okay, the creatures are going a different way. Let's drop them into here. We'll come closer, we'll drop creatures into that node. It's still quite perfect, and I'm quite pleased to see it, even with this number of dots and quite small array, which has almost no impact on the memory. Even with this number of resolution and dots, we have quite very good results. Of course, this node has its own resolution, etc. And finally, I mentioned how the creatures dissipate themselves, so that they don't take one single waypoint. For this node to get to that one over there, it would be best to pick this waypoint and then that waypoint. But the creatures register themselves to the entities of my mediums, which control those waypoints. They register themselves to each waypoint, and then the consecutive creatures that follow through the same connection, through the same medium, will try to register themselves upon this waypoint. But if there are already other creatures, and many of them, creatures will tend to go to the neighboring waypoints and scan to the right and then to the left for the most appropriate waypoint. So if this main one gets filled by 2 creatures, then this one on the right will be filled by 1 creature. The following creature will come, and it sees that, okay, this one is 2, this one is 1, then perhaps I should put myself on the good one. So it will become 3 and 1, next one will be 3, 2, the next one will be 3, 2, 1, and so on. And then they deregister themselves. So as they are going through the paths, if we deploy many of them, and let's pick this node, copy its name to be the target node, and deploy many creatures, they will tend to pick different waypoints, not to clutter the paths and to behave more nature-like. The more waypoints there are, the longer the bake will take, but then the more options for registering creatures will have. I will show you what happens in here. This is my database. This is the file which contains information about all the nodes, about all the mediums and their relations, and also the creatures during the runtime. It is a dictionary of dictionaries, where we store a dictionary for every single scene. Those smaller dictionaries for the scenes control information about the nodes and the creatures, which are also dictionaries. So I had to go through lots of serialization, since Unity doesn't serialize dictionaries. Dictionary is just a collection of keys with their values. So if I enter, for example, if I want to access node number 5, I enter this as a key and I get an access to the node entity, which is an ether. It's a virtual thing. For example, here is node, some sort of node 477, which has almost nothing to do with those visual things that we see in the scene right here. It's just a beacon, it's just a representation. All the information goes into the appropriate dictionary of dictionaries and gets stored and stashed into here. When we're adjusting the zone, we're actually manipulating the variables inside of this file, which then gets altered and transferred back to this entity which we see here. So if we mess up information in here, this beacon will be just reflecting it. We don't have any impact on the visual thing in here. It's just for us to see and interpret how the information is stored in those entities. Medium, which is in here, medium object, contains 6 endpoints of waypoints. For example, you can see that an elevated medium right here. There are 3 mediums and they have 6 endpoints, which are all reflected in those arrays. There is a queue, and the creatures can register themselves and deregister. Of course, it can't be negative, but that's how they do it. And it stores information about which node is connected, which one is the first, which one is the second. It contains equation informations about the slopes, etc., and so on. And also, because I'm running out of time, the final thing that I want to talk about is how the creatures find themselves within the zone. Here, if we adjust this zone, please notice how the gray area on the floor is shown. What I'm doing here is for the creature to find out if it's inside of the zone, it has to first of all find if it's inside of the square, if it's inside of the convex shape, and then if it's below or above the planes. To find if it's inside of this convex shape, if it's a non-square and non-parallel to the world, we have to make use of some sort of structure, which is a number of slabs. Here we have 2 slabs. We have this one right here and that one right here. If we insert a segment, for instance here, we draw a line through every single segment parallel to the Z axis, and now we have 3 slabs here. And we have to find out which slab we are in by doing a binary search, so we can achieve that information with log n time, and then we can quickly check if our Z value is higher than the one of that segment at this particular coordinate. And if it's below, then we should check if we're above that segment. If we're above that segment, then we must be inside of the zone. Then we can proceed with checking about top and bottom planes. But as we're adjusting this structure, All of the binary search trees are being recompiled. That is, my slabs and the data is being recompiled. All the planes are being recompiled by my codes as well. The mediums stretch themselves out so that the waypoints get spaced out by an equal distance and keep the correct values between themselves, the distances, so that the system can maintain its structure as intended by the user. One drawback which the serialization of Unity imposed on me was, in current version of program, it's not possible to Ctrl-Z anything or to delete a node. If we delete a node, this will ruin the whole structure, since I was not able to capture the event of Unity when the user presses delete button. Unity does not handle this event and does not notify me when the user presses delete button. So I'm not able to capture this event and process and remove nodes structures from my dictionaries. I'll be researching about that, and since I'm gonna probably continue working on this artificial intelligence, since I want to present it on my YouTube channel, I'll be doing heavy research on that, and I'll try to find out what would be the possible way to enhance this system and to add this improvement. What would be an additional improvement that I would like to provide here? Well, I would want to do alternative paths. So even though creatures can dissipate themselves and pick alternative mediums and the waypoints, they do not really look globally on the structure to pick the right branch, for instance, instead of the left one, if the left one is cluttered. But I would need at least 2 more months for that, since I have to find a correct way for the creatures to figure out efficiently which paths should be picked and why. Because we did a bake with a value of 6, with a depth of 6, that means that all my previous bake was cancelled. And now every single node only knows about nodes which have length of 6. So it cannot, this node at the bottom doesn't know about the ones on the top. It only knows about the ones in the range of 6, since that's the bake that we performed on the other series of nodes, which weren't connected to my previous system. But with that in mind, I'd like to thank you for your guidance, and I hope you liked this project. I'll be working on it further on. Overall, I'm quite happy with how it came out.